Welcome to yet another exciting installment of the EpicEarth podcast. If you're someone with a thirst for knowledge in the realm of STEM and you're curious about the interesting and quirky experiences in the world of research, you've landed in the right place. This is episode number 25, Blast from the Raft. So don't forget to hit that like, follow, and subscribe button, then kick back, unwind, and prepare yourself for an exhilarating voyage around this epic Earth.
I found it all so fascinating, just learning all the information.
Nobody told me I couldn't do it, and I loved it.
And now I know how to learn. Like, this is a doable thing.
You know, that's an impact that we can't ignore.
Hi, everyone. Welcome to another episode of EpicEarth. I'm your host, Ashley Bosa, and with me I have my co-host, Brian Rosenblatt.
Hey everyone, happy to be here.
And today we have a very special guest. He's a fourth-year PhD student at Boise State, working in the isotope geology lab, and he's a geochronologist. And what that means is that he specifically looks at how we tell time in the stratigraphic record. So he's going to tell us a little bit more about that, but I'd like to give a big warm welcome to Thomas Farrell.
Awesome, thank you. Happy to be here.
Thanks for coming, Thomas. So we'll start off with just getting to know you a little bit better. So tell us a little bit about yourself. What makes you Thomas?
And now,
what makes you you?
Oh gosh, yeah. Hobbies, I don't know. Yeah, I do a lot of outdoor activities, I guess, would be mountain biking, road biking, hiking, running. I like to play music, piano mainly. Took piano lessons for like 12 years.
Wow. Oh gosh.
Classical piano music for 12 years, and then now I've messed around on a guitar and I have a ukulele. So I kind of mess around with those a little bit.
Cool.
Especially in the winter months when it's too cold to go outside.
Nice. Yeah, well, we're looking for people to join our jam band that we're putting together.
EpicEarth Jam Band.
Really?
It's in the works.
Yeah. We tell this to everybody, so at some point we're going to get everyone together. And
okay, well,
yeah.
That sounds fun.
It's just a matter of interviewing the right people. We need the instrumentation, so we're filling it in.
All right, we're down for keyboard mainly.
Keyboard, cool.
Or like rhythm guitar.
I don't think we have a keyboard yet. Yeah.
I don't think we do actually. We're missing a drummer though, probably.
Mm.
That's true. Yeah. I can't drum to save my
I
life, so.
can't do that. I tried.
We'll just throw Ashley on whatever we're missing though. It'll be fun.
Triangle.
Yeah.
Yeah, cool. So you do a lot outdoors. And is that what specifically got you into geology, or?
Kinda. I've always kind of been interested just in like the history of the Earth itself and cool rocks and minerals. I originally wanted to go into like astrophysics or like astronomy. That was like my original. I was like, oh, science, cool. Let's look at space and like stars and galaxies. Those are fun.
Yeah.
And then when I originally went to community college before getting my undergrad, that semester they didn't offer astronomy. Instead, they had earth science. So I took that instead, and I was like, oh, this is really cool.
Oh, nice.
I was like, yeah, this is kind of fun. And I also thought, I was like, the problem with astronomy is you spend all your time. Well, this is me. I don't really get into it deep, but you don't really get to pick up anything. You don't get to pick up a chunk of the star and look at it on a microscope.
Chunk of a star.
Everything is just on computers, which is still pretty cool. In fact, that's what I do now, maybe.
Yeah.
That's what you
Yeah, but there's very little. But yeah, I was like, okay, I like maybe a science where you actually pull some stuff and pick it up and examine it, rather than just looking at it from a billion miles away.
Yeah.
But so I took geology classes, kept taking them, and I was like, well, you know what? When I transferred to my undergrad, I was like, well, let's just keep doing geology. Let's see how it goes. And I've just been kind of enjoying it. So it wasn't really a big master plan. I feel like I just keep like falling in.
Yeah.
So after that, I was like, oh yeah, well, I guess I'll go to graduate school for geology. So then I went to a master's program, and that's where I got into geochronology. That wasn't really my plan either. I was like, oh yeah, this place looks cool. And he's like, oh yeah. My project there was dating garnets instead of zircons, so a different mineral, but the same basic method. Mm-hmm. And so I did that for a couple of years, and I was like, okay, cool. And that school didn't have a PhD program, so I was like, okay, well, PhD might be kind of fun. So So I kind of find my way here to
PhD might be kind of fun.
So nobody ever got
that was
Yeah.
that was a little naive on my part.
Yeah, I think we all trick ourselves into thinking that at some point. We're like, you know what, the PhD won't be that bad.
No, it won't be that bad. Yeah, so then...
It's the type 2 kind of fun, right?
Absolutely, yeah.
Or
fun.
type 4 or 5.
Yeah, whatever. Yeah.
However many years it takes you to complete it, that's the number.
But yeah, before coming in, I'd never even really thought about Boise or Idaho. Being from the East Coast, Virginia, it's like, I don't know, it's like... Do they have towns out there? No, it wasn't that bad.
No, that's true. I didn't think about Boise as a place to live until I started looking at PhD programs.
Yeah, definitely. And I didn't know what to expect, and it's fantastic. I really like Boise a lot. And Idaho itself is...
Was your master's back east?
It was in Boston.
Okay,
Yeah,
so you're very east
Very
coast.
east, yeah. I went to Virginia, then I went even further east for a little while, and then all the way across the country.
That's really cool. Just what are your thoughts about the West in general? Like,
let's see. So I have, I like the West. I like the landscape and the climate. I don't. Well, I guess the landscape.
Yeah.
Is the thing. And the mountains are pretty awesome.
Yeah.
I do like the mountains back east as well. I always get a little protective of them. People are like, oh, East Coast mountains, those aren't mountains, those are hills. I'm like, well, hold on here.
Yeah, like you wouldn't hike through them necessarily. It's not an easy hike necessarily.
No, not at all. They're beautiful
Yeah.
in their own way. A little older, you know.
Yeah. Definitely older.
Definitely older. Yeah, you know, they're not new. They're old and wise.
Yeah.
Had their years, but yeah.
Yeah. Would you ever consider moving back to the East?
You know, yeah.
Yeah.
Maybe, I don't know. There's aspects of it I enjoy.
Mm-hmm.
I like, the big thing I miss is all the thunderstorms you usually get back east.
Yeah.
You don't get, well, I guess here in Boise, you just don't get any storms.
Yeah.
I kind of miss, like, the afternoon thunderstorms that
Yeah.
roll through. Especially from Virginia, pretty much from, like, May to July, almost every day. A thunderstorm rolls through.
Yeah.
And it's just, I don't know, it's just kind of fun.
Yeah, that's funny. It's true because like Idaho and Boise especially don't seem to have like those big monsoonal thunderstorms like Colorado does. We get them every summer, and like other places like Arizona, like a lot of the other Southwest like type of like areas.
They're just like pinned up against the Cascades, so the Cascades just wrings all the water out.
Yeah.
And then,
Yeah, it's a weird climate here. Like, it's got some of the Pacific Northwest, and then it's got some of, like, the Midwest. Like, it's a weird climate altogether.
yeah, that was definitely me getting used to was how hot and dry it is in the summer. I was like, because I moved here like August, and it was like, you had to, like, purposely walk on the shady side of the street.
Yeah. Yeah.
And I just remember my eyes being so dry all the time, and, like, my nose, and I was like, oh, my God.
And that's nothing, really. I grew up in Vegas, and it's, like, way hotter over there, way drier.
Yeah.
I wish it was that hot here in the summers.
Oh, wow, okay, yeah.
It's nice for swimming and
Yeah.
the Boise River and stuff.
Yeah.
There's like usually 2 or 3 days in the summer that like reach over 100 degrees, I feel like. And those are the nice days for me.
Oh my God.
What I do love is the long evenings here being
Yeah.
the way really should be Pacific time, but
we really should be.
Yeah.
It's so weird because I have a ton of family in Vegas and they're actually more to the east
Vegas
than
is,
we are.
Yeah, east of us.
Yeah.
It's really bizarre because like
Yeah.
I heard that it does that so it keeps Boise because of the Mormon population the same time zone as Salt Lake City.
That would make sense.
I mean, I like it because it keeps our evenings even longer.
Yeah. But then there's like Lewiston and Clarkston where they're on, I think they're both on Pacific time.
Yeah.
So there's
like
parts of
nook.
Idaho that are still on Pacific.
Yeah.
Yeah, it's bizarre. But no, I do love it in the summers when you can, be working till 5, 6, and you still have another 5 hours of daylight.
Yeah, to go do activities.
Oh, God, so
9 o'clock,
Go take a nap and then get up and go do something.
Like 11, still late. And I also kind of like the dark mornings in the winter as well. It's kind of, I don't know, I just feel more productive. Even though it's, 8 o'clock, I feel like, I'm like, wow, I'm up early. It's still dark.
Yeah.
I don't know, trick my mind into thinking.
Yeah. But then, in the summers, though, it's, like, really light, like, at 5 a.m. And then you're like, I'm ready to go. Like, let's do this. Yeah. Cool. Well, we're glad to have you here.
Thank you. Yeah, I appreciate the finally getting this going after a couple
Attempts.
attempts.
Yeah.
Well, we made it work. That's the main thing. So I'm like to ask you a little bit about your research now. Can you tell us a little bit about what it specifically you're doing in terms of geochronology?
Yeah, sure. So I'm on this NSF-funded project that is looking at trying to use geochronology to constrain the timing of kind of a lot of different things, but mainly different changes to what we think of the Earth's atmosphere and the biosphere during the Cambrian period, about 495 to 500 million years ago. Because here in Western North America, we have a fantastic exposure of rocks of this age. So the Cambrian is famous for the Cambrian explosion, this massive evolution of life. Pretty much all life body plans, 5 fingers, arms, legs, biaxial symmetry, whatever. All that stuff develops in the mid to early Cambrian. But we don't really know how long that took, or when that happened, or how long it took to happen. And also you have these massive changes in sea level rise, massive events pouring oxygen into the atmosphere. All these rapid changes to the environment are happening. And all that is recorded in rocks, mainly from the Grand Canyon. So that's my biggest field area is the Grand Canyon, because the Farrel River nicely carved us a big stratigraphic section.
Nice.
Yeah.
Starting in the Permian, but cutting all the way down to the Cambrian and then into the 1.7 billion year old basement rocks, even further down below.
So
But there's this really crazy break between the deep billion-year-old metamorphic rocks and the Cambrian rocks. That's a transition between the Proterozoic and the Phanerozoic. So you suddenly have life happening in there, kind of in that zone. And it's where the sea level just drastically rose. That's one thing we're trying to constrain, is how fast did sea level rise in the Cambrian to flood the continent and kind of deposit all the sand, but also in that same time you have trilobites, these little bug-like fossils evolving through that time, and their evolution is so quick and rapid that we can use them to kind of put relative timing on things, but we want to use geochronology to actually get a precise numerical age on how fast these things are happening.
Yeah.
And what's kind of tricky is that most places, well, not most places, but a lot of places where you go to study, you date an ash bed. You're like, okay, this ash bed from, some Cambrian volcano, puts an actual pin in time in that rock. But the problem with Western Laurentia, I think of it as Eastern United States, there are no volcanoes. So you can't put any exact pin on time. We have to use detrital minerals and detrital zircons to get what's called a maximum age. And so it's interesting. So think of it as kind of one of the, we usually, you think you learn in Geos 101, the fundamental Steno's laws, superposition, inclusions, cross-cutting relationships. So you use superposition, so the rocks at the bottom have to be older than the rocks at the top, otherwise how'd they get there? That's a basic logic thing. And the other one is that anything included in another thing has to be older than the thing it's included within, if that makes sense. I kind of said that really awkwardly. So basically, if you have a detrital mineral a zircon that crystallized in some pluton or erupted some volcano, then got eroded into the sandstone, and if we date that mineral, it's older than the rock it's incorporated into. And so that's our kind of way to get around not having any direct dates.
Wow.
You have to use a maximum, and they're kind of, they can be both frustrating and useful in that they give you a maximum age, but it doesn't tell you what the minimum age could be.
Okay. So there's still some error on the minimum side of the age, but
luckily we're getting dates that are much younger than the last 100 years of so most things down there are constrained by trilobite biostratigraphy. So they look at the evolution of trilobites and then they say, oh yeah, these zones are correlate with these zones, and over in Europe they're dated at 504 million years old. So we'll correlate that over and say this is also 504.
Yeah.
But we're showing that I just got a zircon in there that's 498 million years old.
Yeah.
So something's wrong.
Yeah.
And so that's how they also another big part of this project is to kind of what they call like calibrate the time scale. So every 8 years, this group publishes the geologic time scale in these like 600-page volumes.
Yeah.
And so it goes from everything you learn in Geos 101, Cambrian, Jurassic, Triassic. I didn't do those in order. All the way up to the Cenozoic. And it's just big. Like they break them into little subzones and all that kind of stuff. And so every 8 years they try to build up,
Wow.
refine that.
Yeah.
And so the Cambrian is still pretty poorly dated. And so that's one thing we're trying to do now is trying to like refine the global Cambrian time scale with these rocks from the Grand Canyon, and also I've done some stuff in Utah and Nevada and potentially parts of California have they're really great records of life evolution, sea level rise, carbon stratigraphy, but they have no real dates because there's no ash beds to date them, so it's kind of like a tricky thing.
Wow.
Trying to.
Yeah, that's really fascinating. I love hearing about stories like that where, it's like rocks aren't just something geologists like to lick, like we'll just look at, but they actually tell a story about how the Earth formed and what happened in Earth's history and, before even like recorded history, right? There's so much information that is just like held up in like these.
Yeah. So let's say like the stratigraphic record is like a book, and it has like, written on the pages are, if you can read the rock, right, you say, oh yeah, sea level rise happened, and then like evolution.
Yeah.
But it has no numbers, no page numbers on it, and so what I'm trying to do is put like page numbers on this book to be like, okay, this page is 498, and the next chapter is 500.
Yeah.
Otherwise, we don't really know when those are. So
Yeah.
geochronology puts like page numbers or like chapter numbers on the book that's recording Earth history.
Yeah, that's really cool. That's an awesome analogy.
But of course, half the pages have been ripped out.
Yeah, totally.
More than half.
Or they're shredded, or they're like half of it's over here, the other half's over there.
Yeah, like when you look at like a stratigraphic record, you have to think, half of that rock has probably just been eroded away.
Mm-hmm. Yeah.
So, yeah, it's incomplete.
Yeah. Yeah.
It's smudgy. I don't know if you even like from Lord of the Rings when like Gandalf opens up that big book in Moria. It's just like cut and torn and blood stains and the pages fall out.
Yeah. Nice.
So that's this
the
geological book.
Time.
Yeah.
Yeah, nice. Well, good luck with that.
Thank you. Yeah, it's an ongoing challenge.
Yeah, no, that's awesome. And so you look at zircons, and what sort of techniques do you use in order to like research their history and how get dates on them?
Yeah. So zircons are probably the best mineral for geochronology because we think of it as like little clocks, little ticking clocks, but instead of a clock that ticks on seconds and hands, the chronometer is the decay of uranium to lead. Mm-hmm. So through tons of research in the early 20th century, a lot to do with like the Los Alamos Trinity project, we know very well the decay of how long it takes a uranium atom. Well, how long? I guess it'd be like the probabilistic.
The half-life.
The half-life, yeah. So I think for uranium, so there's two isotopes of uranium, 238 and 235, and they decay to lead-206, lead-207. So it actually has two clocks. Mm-hmm. Actually, there's three if you count thorium, but we'll go with two. So they cross-check each other, which is kind of nice. So no other chronometer. Like there's other ways you can date mineral with argon or some neodymium or lutetium hafnium, but they don't have double check on each other. They don't have two clocks that are ticking down, and one ticks slower than the other. But the one we usually use for most, actually all geochronology, is the decay of uranium-238 to lead-206. And gosh, I hope my advisor's not listening to this. When I think the half-life, I'm pretty sure is 4.48 billion years.
Wow.
That's
so
crazy.
Basically, if you had like 10 atoms of uranium, it's a likelihood that after 4.4 billion years, you'd have 5 of lead and 5 of uranium still left. But it's a very pretty well-known decay constant. Mm. Yeah. So what we do is we take our little zircons, tiny little things, like you can't even see them. I think they're I like to see them about the width of a human hair and maybe just a little bit longer. They're tiny. Mm. So we usually use microscopes and little tweezers and little pipettes, and you're like moving them around. And there's different ways to date them. We actually date them 2 ways in our lab. First is we'll zap them with a laser. So a little laser will, it's actually kind of fun to watch. You can watch on the screen, the laser like pop, 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 drills a tiny little hole, about a 25 micron diameter hole.
Wow.
And what it's doing there is it's pretty much, vaporizing and ionizing all those atoms, and they get sucked into a mass spectrometer that is counting, the uranium to lead ratio.
Mm-hmm.
And so that's how we get, assuming all the lead came from the decay of uranium, which is an assumption that we check, but it's a pretty well-known one, that zircons don't like lead. It's like, get the hell out of here. I just want the uranium into their crystal lattice. And so that's one way. It's a pretty imprecise way because we're counting the uranium and lead atoms for about several nanoseconds, a couple milliseconds.
Mm-hmm.
So even in that time, you're still counting like a couple 100,000 atoms of uranium and lead because there's just trillions of them. So you get a pretty kind of a rough age. I can say from the laser that, this zircon is 495 million years plus or minus 25 million years.
Yeah.
So
Wow. Yeah.
it's pretty big uncertainty, 25 million years. Like that wouldn't tell me anything. Like the whole Cambrian only took 50 million years, which is pretty short, 50 million years.
Yeah.
Not a lot of time depending on what scale you're looking at. Now if you're looking at volcanoes erupting, or like lahars,
Yeah. That's much quicker.
it's
but
much
yeah,
quicker. So the time scales are a little different. But there's another technique that we use. So that technique is called like laser ablation because you're laser ablating with the zircon. And then if we really want to know how old it is, a much more precise age, we take it into our clean lab and we fully dissolve it. So we're not zapping, where we dissolve the crystal in hydrofluoric acid at high temperatures. We put them in a little metal jet called bomb. So you heat it under pressure and temperature to completely dissolve it. And then we go in the lab and we use some different techniques and we isolate out just the uranium and just the lead because we don't want the zirconium, the silica, the hafnium, all that other crap that's in there that's not useful for dating. It's useful for other things. And then we load that, a teeny little drop of it, probably like a speck of dust. You wouldn't even hardly see it. Sometimes you can't even see it in the beaker. But we stick it up and we load it onto a little metal filament. And then that filament goes into this machine. The ones you can see on the 5th floor, if you look in the window, you see those two big.
Yeah.
Those are called TIMS, thermal ionization mass spectrometers. And so instead of laser ablation, this is thermal ionization. So you load it's basically a salt. Think of it as like a salt chloride of lead and uranium together on this little, think of like a light bulb filament. Then you heat it up. And usually to heat it up, it's going at about maybe 12 to 1500 degrees Celsius. Whatever that is in Fahrenheit, like 3,000, 4,000 degrees or whatever.
Yeah.
And so that's hot enough that you are vaporizing your lead atoms and uranium at different times. But first we'll do lead. And it's so hot and so energetic that it ionizes them. It volatilizes them and ionizes them. It strips off the outer electrons. Now they're positively charged particles. And then they're accelerated with like I think a 25 kilovolt acceleration down over a magnet. And so they're bent around a corner. That's if you look at them, they're like a 60 degree thing. And so it throws the atoms around a magnet. And the lead, there's 204, 205, 206, 207, and 208.
Yeah.
And so 204 being lighter is flung at a sharper angle, and 208 being a little heavier. It's what's that, like an inertia or like?
Yeah.
Or a physics professor. It's like
yeah, it would have more.
What's the word I'm looking for?
Well, it has more inertia.
Inertia, yeah. So it takes more to bend it around.
Yeah.
And so I still can't believe this machine was developed. It's just insane.
Yeah.
And then around the other side is the detector, which is placed in the right spot to hit only 204, 205, 206, 207, 208. They're placed in the right spot based on the equations of the magnet. And we just count them, and they're counted. Like 1, 2, 3, 4, 5, 6. But it's counting, I think on a good ionization run, you're counting about, it can be up to 1 million counts per second.
Whoa.
Of 206 of your major isotopes. And so instead of the laser, which is counting maybe a couple 100,000 atoms for like 10 nanoseconds, we're now counting lead atoms at usually about a couple 100,000 counts per second for about 3 hours.
Wow. That's a lot
And
of
this
data.
is all from just one tiny
zircon.
Oh my god.
So I think I've calculated before, I don't know. So one tiny zircon, even though they're tiny and small, has trillions of lead atoms
That's crazy.
in it. And so now it's basically just counting statistics. We're just counting so many times that we can really precisely know the ratio of these different lead isotopes.
I have a string of questions for you. Well, first, how do you isolate your zircons from everything else that you have?
So the actual zircon crystals?
Yeah.
Yeah, so that's also a whole other process. So let's say we'll take a rock. So from the Grand Canyon, we pick up a rock. It's a sandstone. And then we go into our first floor. We have our crushing lab. And so there's this big jaw crusher. That'll be a good sound effect. And it crushes it to like gravel. Think of it like kind of like gravel size.
Okay.
Like maybe like a nice fine gravel, like you see on a gravel road. And then that then gets taken to the machine called a disc mill, which has 2 rotating disc plates. And they have some design in them, kind of like a flower-like pattern. And there's a hole, and so the rocks fall into the middle of this thing, and then it pulverizes them as it comes out. And so that gets you down to like a nice sand, like a nice fine sand. And then, so now you have basically you've taken your sandstone and you turned it back into sand.
Yeah.
Or you take your granite and you turn it into something that's sand size. And then that gets taken over what's called a water table. So you pour it over this if you ever see, it's like the blue table in there. It has grooves on it. It kind of shakes like this. And basically it's separating out by density. So light things fall down and heavy things stay up. And so zircons are very dense. They're one of the densest minerals. And so that's one way to kind of coarsely separate into a light, a more dense and a less dense fraction.
Yeah.
And you take your dense fraction, which is usually like, like a half a cup full of stuff. Well, you've taken like, a quart, you have like half a cup or less. And then that gets taken, so then we go upstairs in another lab and then we use a magnetic technique, which is called a Franz.
Okay.
It's really cool. It's like two slanted slots with a magnet. And so anything that is non-magnetic falls down and goes in the lower slot. Anything that's magnetic stays up high. Okay. So zircons are non-magnetics. This is the way to get rid of like all your iron, all your dense iron minerals that you don't want. And so from there you're left with really depends sample to sample, but you can be like a tiny little bit left of that's your dense but non-magnetic stuff.
Yeah.
And there's one more step still to get your really dense materials. And that's where you use like heavy liquids. So there's this liquid that we use for zircons called MEI, methylene iodide. And so I think its density is like 3.32 grams per cubic centimeter. So really dense. It's wild. You'd like pick up this bottle of it.
It's just
3 times denser than water.
3 times denser than water, yeah. And so zircon being really dense will sink to the bottom of that fluid and the other stuff floats on top.
Nice.
And so by that point you've taken a rock maybe the size of a basketball, and now you have your zircons, which is you almost can't even see. They're just like a tiny little pile. Probably still a couple thousand of them down there.
Oh my god.
But yeah, and then we take those into our other lab, and that's when you like pick them out. You pick out the good ones, you want the nice, clean, sharp ones, and then we usually mount them in epoxy, so they're easier to deal with.
Oh yeah.
You can look at them, you can polish them, and all that kind of. There's all like bunch of other like analyses you can do on them. You can take SEM photos of them, look at their trace element chemistry on the laser as well.
Yeah.
All the microscopic things.
All microscopic things, yeah.
It's so cool. It's fascinating.
Yeah. So those machines, they have to be so sensitive to be and also like have the ability to record like a ton of data if they're doing like millions of counts.
Yeah, the machines themselves are crazy. The TIMs themselves are I feel like such almost they're not overly engineered. That's a bad thing. But they're so perfectly engineered to do just one thing.
Yeah.
It's just they do that one thing really well.
Yeah.
Yeah, they're crazy. Yeah, they're constantly running. You can't turn them off because they have to be held under vacuum. Like the analyzer is held to like 10 to the negative 9 vacuum all the time, like every single day that it's ever been running.
Dang.
I heard one time someone told me that they overheard someone talking about something saying that our lab uses the most power of any lab in the university.
Yeah.
Because also the clean lab has to be, like the ceiling is just all HEPA filters. So the air is always being filtered.
Yeah,
everything's always on.
Yeah.
The pumps can never be turned off.
Yeah.
So,
oh my god.
That's crazy.
It's all coming from the 5th floor.
I wonder how that compares to like the Boise State supercomputer. How much energy you use
that's
compared
true.
to that.
I don't know. Yeah, that'd be because there's a lot of just like a lot of mechanical pumps, things that just take a lot of energy to move around.
That's fun. That's so awesome. Well, yeah, thanks for sharing all of that. I mean, it's so fascinating. I don't know a lot about
me neither.
Like geochronology, like the fine microscopic stuff. So it's really fun to hear about the research that you guys do.
Yeah, one thing I didn't talk about, but the reason we go in the clean lab is that we're trying to measure lead.
Yeah.
Very tiny amounts of lead very precisely, and we know from all the great work in the 20th century with leaded gasoline. I mean, work in a bad way. There's like lead everywhere.
Yeah.
Like there's more lead in one strand of our hair than there is in the zircon.
Oh, wow.
And so we have to go in there and try to get rid of all the environmental contaminant lead. And so, but luckily, kind of luckily and unluckily, there's 4 isotopes of lead. 206, 207, 208 come from the decay of uranium and thorium, and 204 is just naturally occurring. It just was there since the dawn of the universe. And so any 204 is contaminant lead. Like it wasn't part of the zircon.
Yeah.
And so we monitor that isotope to look at what's called our blank. Like everyone has a blank. Like how much lead did your body, and your sloppy technique bring into that beaker where the zircon is? And it's still a tiny amount, like a good blank. Like in our lab, like a good blank is about 0.1 picogram of lead. So 0.1 trillionth of a gram of lead is good.
Versus,
but like 1 picogram is kind of dirty.
Versus like how much is in the sample?
Yeah, so it really depends. Like you at least want like a 10-to-1 ratio.
Okay.
And 100,000 is better. So it could be, depending on how big the zircon, you could have, like a nanogram of lead would be a lot.
Wow.
So a billionth of a gram of lead is a lot of lead to measure.
Yeah.
Usually you're measuring, like 20 or 30 picograms.
Wow. That's crazy.
Yeah.
That's nothing. Well, no wonder you can't really see it. So.
Yeah.
Do you have to wear like protective equipment?
Yeah, we were like our classic white lab coats, gloves. Sometimes I wear a hairnet now that my hair's got kind of long. Maybe it just falls on my face. And I'm just like, One thing that was crazy that you could see in your blank is how sensitive it is. I used to wear glasses because I ran out of contacts. I wear my glasses, and I can't look through a microscope with glasses on. It just really annoys me, so I have to take them off. And so I take them off, look at the microscope, do my thing, put them back on over there. And my blanks are really good. And then I started wearing glasses, and they weren't as good.
Yeah.
And that's because I was slightly touching my face. Over my glasses, and so I was getting a little bit of lead on my tips of my fingers.
Wow.
And that you could see that by an elevated couple trillionths of a gram of lead.
Oh my gosh.
Just from off, like this, on your dandruff or whatever.
Crazy.
I was like, I guess I need to get contacts again. So I would also do the thing where you push them up.
Yeah.
And you
all the time.
Yeah. I've had that issue before trying to look through a microscope.
I know some people can, and I just can't look through. And also I had scratches.
Yeah, totally.
Well, your glasses change the focal length of your eye, and the microscopes are not really meant for you to have an extra lens in front of that. So.
Oh, okay. Yeah.
But
in
theory, you should just, even if you need glasses, you should be able to put your eye, unless you're farsighted where you can't see close up. Because even though, you should be able to take your glasses off.
Oh yeah.
See
I can see without my glasses scope, but then I go up and then I can't.
Yeah, true.
I'm very nearsighted. I can't really see.
Same.
Yeah.
Totally.
Just feeling around the lab for your glasses.
I'm on the scope trying to work, and then when I have to go move things around, I can't see, so I put my glasses back on.
Then you're
I have to take them off.
Yeah.
It's just...
That makes sense.
Pro for contacts.
It's also really annoying. In our hood, everything is either white or clear. And so depth perception is always gets
really
me.
Hard,
I always have to put my hand.
How many windows have you walked into?
I know. God, can we get some color in this place? Everything is white or clear.
Frosted
so
glass. Frosted glass or something.
It's all blurry. I just don't even know. That's really funny. Well, you've told us a lot of fascinating stuff about your research. So I want to ask you about what the most fun thing is about what you've done.
Definitely the most fun thing is the cool places I kind of get to go to collect these rocks.
Yeah.
And so, fortunately, I was lucky enough to be on this project, NSF project, in the Grand Canyon. So we've gotten all the permits and whatnot to collect rocks in a national park in the Grand Canyon. And the most fun thing is that the best way to get around the Grand Canyon is just to raft through the Grand Canyon. And so, yeah, that's what I've done now, I think 4 times, is that from here, my advisor and I, we drive down, and, you park at the entry board to the Grand. Once you get on the river, there's only 2 places you can possibly get out.
Yeah.
They're 225 miles and 280 miles downriver.
Oh my gosh.
So there's no way out once you get in there by boat.
Yeah.
You take a helicopter.
Yeah.
And so, yeah, it's awesome. These trips are usually like 10 to 14 days long. And we have these huge rafts. There's these big motor rafts. They're not rowboats. And so they're probably like the size of like a van.
Oh,
and so
wow.
each one fits maybe like 15 to 20 people. And then all our gear.
Yeah.
And so we, just get on these boats and go down, float down the river, and you stop, collect rocks, and camp along the river, and then it's just really awesome down the Grand Canyon.
That sounds like just an excuse to go rafting
Yeah.
down the Grand Canyon.
I think that's half the reason why some of these people are like, oh yeah, I'll stay at the Grand Canyon.
Yeah.
Just raft through it.
So do you have like specific targeted spots that you're aiming to get samples from, or do you just like find spots along the way?
Yeah, it's kind of a bit of both. A lot of these so for my work, for the trail zircons, they need to be paired with some type of fossil occurrence.
Yeah.
Otherwise, we don't really know where they are in stratigraphy. So a lot of it is just, so we go there with like fossil experts. We have this guy in our research group. It's like an expert in
From Boise State?
No, he's actually he's an old retired high school teacher.
Oh, cool.
Who was, he got his PhD, in paleontology trilobites, but then he just taught high school for 20 years. But he's written tons of papers. He's pretty much one of the world's experts on these Cambrian trilobite fossils. Wow. Yeah, he's a really funny old guy, kind of like an old cantankerous old man, but he's really funny. So he comes down and we'll just stop and he'll be like, let's take a good spot. So we just pull over and he just digs through the shale trying to find some fossils. But there are some locations where we, some famous side canyons, we're like, okay, this is a good section, we're going to hike up here. And one of probably the craziest one was the second trip I went on. We did a 2-night side excursion up this side canyon.
Oh, cool.
And so we, I always say it's probably one of the more remote places I've ever been, because we had to get on the Grand Canyon, and then we had to float down the river for, I think it takes 2 days to get down there. Wow. And then we parked the boats. Then the small group, myself and I don't know, there might have been 5 or 6 of us, did this 10-hour hike. I don't even know how much elevation gain we have. We just basically there's no trail either. Just up this super steep, super sketchy side canyon. It was one bad fall and you're just falling, rolling hundreds of feet down. I was like, God, what am I doing up here? And we had to carry all our water in and all our food because there's no water up there. So I think each person, we actually had 2 people on that trip. Their whole point of that trip was to carry water in and rocks out for this side trip.
That was their whole purpose.
That was their whole purpose of the entire trip. And they have 100-liter bags, and they're carrying, I want to say how much water they're carrying. I think I was carrying 15 liters of water.
Sheesh.
Just 35 pounds of water.
Yeah.
And they were carrying maybe double that because that was
Oh
their
my
job.
gosh.
Yeah, and so it was just 10 hours of hiking. I don't think we even hiked that far. I think we averaged less than a mile an hour.
Because it was so steep.
It's so steep and
Oh my
just
gosh.
zag up.
just zigzagging all around, yeah. Then we get up there and we spent 2 days in this kind of side canyon area. And I remember it was May, and I remember the our trip leader was oh, don't bring a tent. It was you'll just need a sheet. It's gonna be hot. And it was 30 degrees at night. And I remember it was just no one had tents. So we're just roll up in a tarp, freezing cold at night.
Yeah, that sounds terrible.
Yeah, it was very memorable. I guess that would be was that the type 2 fun?
Yeah.
Exactly. Yeah, was that fun at all?
Oh my God, the hikes was so miserable.
Yeah.
The hiking back down, all these rocks.
Yeah.
Yeah, see, that's not, when you hike up a volcano, the hike up sucks, but usually the hike down's so much fun because, at least in Villarrica, we could just slide down the volcano. Stromboli, it just has a nice big patch of ash that you could just you could literally just fall down it.
Yeah.
Forward and be totally fine because it's so soft. So,
Yeah.
But no, it was really fun. It's such a spectacular place.
Yeah. So cool.
They're crazy things. Yeah, going through all the rapids is really fun.
Yeah, I bet.
Yeah.
Is that like one of the best stratigraphic formations you've seen?
Yeah, it's one of the, what's
Most
kind of unusual in, at least in stratigraphy, is having a section that runs on. So usually, like, you'll go to a canyon, like, oh, here's a section of the Cambrian. And it'll be like, but there's no lateral continuity of it.
Yeah.
Grand Canyon is a place where the rocks are exposed laterally for several hundreds of kilometers.
Yeah.
And so you can see the lateral change. Anywhere else, you'd be like, okay, there's a column here, and then 10 miles away we have one here.
Yeah.
But what happened in between?
Yeah.
And here you can see that change happening.
It's cool.
All the way through. So you can see, the sandstones, getting thicker and thicker, and then you can see the shales transforming into limestones as you get out into the ocean. You're basically going from the coastline out into the ocean in the Cambrian. And so, yeah, that's what's... But of course, most of it you can't get to. It's just cliffs.
Yeah.
So you're just floating down, and you're like, oh yeah, there it is way up there. Oh, it'd be fun to get up there, but probably don't want to. But yeah, you can at least see the facies or the change in environments from sandy beach out to shale, shallow marine, out to carbonate, deeper marine.
Wow.
That's so cool.
Facies change. You can actually, see the change. You can track, certain beds. Whereas that's what makes, I think, the Grand Canyon super unique, is that it's one of the only places, I think, where you can have that lateral continuity of the rock.
Yeah.
Through the whole thing.
Yeah, that's so cool. Such a cool place to visit.
Yeah.
Yeah, it's...
Did you go out there a lot, Brian?
No, I've never been.
You've never been?
Yeah.
Oh man, you've got to go.
Yeah, I've been to the I've been to the top of the rim. I've been to the rim once.
Yeah.
One day I was at the rim, and I've been at the bottom for like 50 days.
The Grand Canyon's the Colorado River.
Yeah,
right?
Colorado River.
So I mean, I've been to the lower part of the Colorado River. I've been to like the Hoover Dam.
Okay,
and whatnot, so, but not like the heart of the Grand Canyon area.
Yeah, it was wild. They actually, so originally back when they were building all those dams, they wanted to build 2 more dams in the Grand Canyon and flood it.
Wow.
Oh yeah.
It was going to be Bridge Canyon and Marble Canyon dams. They wanted to dam, and actually, if you float down, you can see where they bore holes into the side of the canyon at 2 spots where they were kind of testing whatever people test for, permeability or whatever.
Yeah.
But luckily, it was only because of this radical I think it was had to do with the Sierra Club back in the 60s. Basically put these big ads out being like, I think their term was, what's that famous church, one of the famous church ceilings, the Sistine Chapel? I was like, would you flood the Sistine Chapel to get a better view of the ceiling or something like that?
Yeah.
Was their thing, because basically it would be flooding.
Yeah.
So imagine the Grand Canyon just covered in a lake. You wouldn't see it anymore.
Yeah.
But it's crazy that they even thought they were going to do that.
That's terrible.
Yeah, so luckily that didn't happen.
Yeah.
They still have Glen Canyon Dam, which, yeah, it would be nice to see what that flooded. Because, there's all these beautiful pictures of all the side canyons that are flooded by Glen Canyon Dam.
Yeah. They use that for controlled experiments, though, don't they?
Yeah, that's the thing about the Grand Canyon. It's completely dam control.
Yeah.
So the water rises and falls every day with the release for the power supply.
Yeah.
And it's getting, even since the last couple of trips I've gone on, you can see the water level getting lower and lower.
Oh, yeah.
And then you talk about these river guides that have, been on there for 30 years. They will point out, oh yeah, it's the old watermark.
Wow.
So
Oh,
it's just
man.
like everywhere in the West, things are just drying up.
Yep.
Yeah.
Yep.
It's just literally going to be a canyon at one point with no
Yeah.
water in it.
Yeah.
Yeah, well, that's awesome that you've gotten to experience that. Most people don't
I
even
know,
get to experience that once.
I know, yeah, I feel really lucky that
How many times have you done that?
4 times.
Wow. Awesome.
Yeah. Yeah, so you just got to show us all your pictures now.
Yeah.
I know, yeah, I have so many pictures of the Grand Canyon.
It's ridiculous. Cool. So that sounds like a lot of fun. Sounds like you've had a lot of fun stories from that. But you've also noted that you had a kind of a crazy story driving an SUV down a really crazy road.
Oh yeah, this was so this would have been, I guess, a couple years ago. We drove down to Arizona to look at some Cambrian rocks not associated with the Grand Canyon. Well, just south of the Grand Canyon. So we didn't have to go float out. You could just drive there. And so it was myself. So Mark Schmidt's my advisor, and then Mike Moore, his other PhD student, and myself. The 3 of us drove down there. in 2 rented SUVs from up here in Boise, drove down. And then as kind of a side thing, we wanted to go collect some rocks for Mike's work on this like super eruptive volcanic sequence or whatever.
Mm-hmm.
And so we picked these really nice, I don't know what it was. It was like some SUV, like a Suburban or whatever. Mm-hmm. And we keep driving down this just back Arizona, like middle of nowhere road, and it's just getting rougher and rougher and rougher and rougher. I'm like, man, this is like, I don't know, this is going to be a little
sketchy.
A little sketchy. And it's just basically like, imagine you're just like rocking back and forth.
Oh, gosh. These massive SUVs.
Massive
too,
SUVs. Yeah. And I remember Mike was joking, like, wow, this car is never going to drive right the same. But yeah, it was beautiful. Got out into this really remote, it was like kind of near the California-Arizona border, I guess. It was just kind of a memorable, like nothing like crazy really happening except for this insane, basically it was a riverbed, like a dry creek bed. I don't think it was really a road.
Yeah.
But I guess people drive their Jeeps down there.
That makes sense.
But it was just, quite memorable. Luckily we made it in and out without any trouble. But
I think they tell you, don't they, in rental SUVs or rental cars, not to be on roads like that too?
Yeah, definitely.
Yeah. Just return and be like, we swear it was just a paved road.
Yeah, they usually have a GPS.
We don't know why the axle's all messed up.
Yeah, they're gonna be like, where the hell is this car in the middle of the desert?
Yeah. Oh, well, that's fun. It's nice to it's always nice to hear people's stories from the fields too. So
yeah.
Okay, Thomas, well, now I'm going to ask you kind of a more serious question.
Serious question.
So I'm going to give you a scientific problem to solve on a terrestrial planet because there might be a lot of geological activity on one of the terrestrial. Obviously, there is on Earth. But I'm going to give you Mercury as a scientific problem to solve on Mercury. So imagine that your orbit around the sun is only 88 days. And so your birthday comes a lot quicker. And but you have 58 and a half days of daylight hours. Wow. So you've got a lot of time to do your research.
Is that because the surface is locked to the...
Is it?
Yeah, I think like the actual, like the spin of Mercury is much, like it takes 58 days for it to spin.
Okay.
Wow.
Yeah. So how would you solve a scientific problem on Mercury?
Mercury. Jeez. A scientific problem. Any problem?
Any problem you want to solve. It can be related to your research, but it can also be like just something really silly too. Like what's the SPF of sunscreen I have to use in order to being so close to the sun.
I feel like it's maybe too literal. You'd want to stay. I assume it's like super freaking hot on the sun side, and it gets really freaking cold on the on the backside. It's like no atmosphere, I assume. So I feel like you'd want to find out a way to somehow have some kind of like whatever you're living on stay right in that probably very narrow area where you're not freezing to death and you're not being fried. And so
just keep walking, like just keep following the space, like where it's light and dark, like
like where it's like twilight or like dawn or whatever. I'm not sure what question that would be though.
What if there were like imagine if there were like a mineral that you could extract from the surface that could tell you something about what Mercury was like in the early ages of...
Yeah, that could be I'm sure there's zircons on Mercury because I think there's like a magma pool.
It's probably all magma on one side.
Yeah, I mean, I know they have done work on the Jack Hill zircons, so the oldest zircons ever found on Earth, and they've elaborated from oxygen isotopes in there that there was liquid water on the surface.
Oh, wow.
So you could try to do a similar thing with Mercury. to see, 4.5 billion years ago or whatever, before the sun got super hot.
Yeah.
That's how suns work.
Yeah.
If there was like potentially liquid water on Mercury and maybe even life, I doubt it though. I think it's just too close to the sun.
Yeah.
Probably didn't have enough time.
Just short time span.
Short. Yeah. Has anybody been to Mercury? And then we went to Venus, right? There was a probe into Venus. Did you go to Mercury?
I don't think so.
Yeah.
I'm not sure though. Yeah. Definitely the Venus one, like, that was it. I mean, it obviously never landed on the surface, but it just like orbited the planet.
Yeah. And Mercury seems like a...
Thanks.
Sorry, sidetrack. Venus seems like a wild place.
Yeah.
But,
Yeah.
yeah, Mercury. Gosh, yeah, the day.
It's just boring. It's
I wonder
the
how-
smallest planet.
Yeah.
Nobody cares about it.
Just let the sun eat it up.
Yeah, I know.
Yeah, one thing I guess I would think about being, thinking about time all the time is, how what your perception of time would be on a planet that close to the sun. So you have a lot of gravitational force. I feel like. So that, doesn't that time dilation?
Yeah, I mean, in theory, your time would probably be moving slightly slower compared to the Earth, but I don't think it'd be too measurable.
Okay.
Because it's all about, like, how fast you're going with respect to the speed of light. And, like, that's still pretty slow with respect to the speed of light. So.
Right, so it would be very small change.
Yeah.
Huh.
But enough, probably.
Yeah, I mean,
for
definitely
you to-
there's... I mean, you get time dilation when you fly in an airplane, so...
Yeah.
Yeah, it's there.
Yeah.
It'd be wild to live on a planet where the day is almost as long as the year.
Yeah, yeah, totally.
Yeah, it's crazy. It's more than half the orbit of the sun. That'd be weird.
Try to make a way for that to be sustainable, where you stay up for all those one full day and then you go to sleep for one full day, and like, how could you exist like that?
Yeah. Yeah.
Be a cold-blooded animal,
Yeah,
probably.
yeah.
Like a reptile or something.
Something that does not exist on Earth.
Yeah. Okay, well, moving on from that question, because that was a hard one, but it's a lot to think about. I'm glad we
Still thinking
circled
about
back to the time.
Still thinking
Yeah.
about it.
So in this next segment, Thomas, we ask you to sort of give your elevator pitch to 3 different groups of people.
Okay.
It's kind of a good way for us to practice our
It's true.
how would we tell our stories to different types of people. So the first one is, how would you relay what it is that you do to a 4th or 5th grade class?
5th grader.
Okay, yeah. Luckily, I actually did do this kind of
Mm-hmm.
a couple times, about 3 weeks ago. I feel like when you think everything in science has been figured out, or we know the Earth has been 4.5 billion years old, and then life emerged like 500 million years ago, but we really don't know that actually really that well how long life took to emerge, and whether it was we like to think that it's happening all around the Earth at one time, but it probably it was happening in different places at different times, and if we get good geochronological constraints, we can actually figure out what the time difference was, maybe between these evolutionary events, or like sea level rise, or different Earth events happening.
That was a pretty good one. I like that.
Okay.
Just going along with that, you did do this little segment with the Denver Museum of Nature and Science a few weeks ago, and so can you just talk a little bit about what that experience was like?
Yeah, sure. That was kind of a cool experience. So it was this, if you want to look it up, it's something called like Scientists in Action, I think is like their program, and so it's out of the Denver Museum of Nature and Science.
Mm-hmm.
I always want to say natural science or natural history, but that's not so they go to different places, different labs and universities and institutions around the country, and they do live broadcasts that get streamed to like elementary school classrooms, I guess, throughout the country. We actually had one from Mexico, so it's like North America.
Wow.
Oh, cool.
And so usually it's 2 people kind of like talking about what they do in their lab settings, and then there's like a question and answer period afterwards where the kids get to ask us questions, and we responded. I was actually quite impressed by all their questions. They were actually some were like, wow, actually, I don't know.
I don't. Good question.
Good question. Yeah. Yeah, and so for our case, one of the co-PIs on my project is a curator at the museum, and so he's like, oh yeah, we should come up and do one about dating rocks. So it was myself and then another master's student on the project at Utah State. Her and I were kind of like co-hosts. It was like filmed up on the 5th floor of the ERB. It was a little, like I'd never been filmed like that before, so it was a little stressful. Because you're sitting there like, okay, like don't itch your face, don't pick your nose, like you're on camera.
Did they do any makeup for you or anything?
No, I was kind of hoping we were going to have like whole hair and makeup session, but that did not happen. But no, it was really fun. We did it 4 times, so towards the end we were getting better at it, but also tired of it. So it was kind of like a balance. But it was really fun.
That's really cool.
I think I would do it again, but it's very exhausting.
Yeah, you're like kind of like Bill Nye, but in real time.
Yeah, I know, no editing. So I was like, I wish I messed that up, or like I didn't say that right. Yeah. But it was fun.
That's awesome. What a cool way to get them interested in different sciences.
Yeah, like every pitch at the end was like, kids, go look at a rock and never know what you're going to find, because we actually don't really know that much.
Nice.
We know a lot.
More future geoscientists. That's what we need. Cool. Okay, well, I'm going to swing it back around to our segment. So you've had some experience with sort of, projecting your research to some younger audiences. So the next audience would be like an undergraduate student, or maybe like upper level high school student, like someone who knows, okay, like I know a little bit about like dating methods and things like that, but I'm not quite sure what it is that you do. So how would you explain it to them?
Undergrad.
Yeah, okay. So I would probably say, So, if you've ever like experienced what's called the sedimentary rocks, so they deposit in layers. So maybe like you've driven through a cross section, you see a bunch of like slanted layers in rock, right? So those, I think of those as kind of like our pages of a book. Each layer, is like a page of a book. And so in that book, if you can look and find fossils and minerals, and if you analyze those in the lab for like different carbon isotopes, oxygen isotopes, the different proxies that tell us about something that's going on, you can kind of read that history in the rock. And what I'm trying to kind of talk about later is that, okay, like actually, here's this like 100-foot section of rock that's recording some change in the environment, Earth history, evolution of life, some carbon, if you're interested in the carbon cycle, some cycling is happening here. But how long did that take to happen? Was it, is this span of rock representing 10 years? No. A million years? 10 million? 100 million years? We don't actually really know. We can get some good idea, You can look and be like, okay, there's average sedimentary rates. So usually it's like, a meter per, couple 100,000 years or something like that. So you have some good idea, but we don't actually know exactly what that is. So depending on what the research question you're trying to ask, you can be, okay, we actually need to go in here and actually try to date these different horizons and see if we can actually constrain the duration of whatever environmental process is being recorded in that rock. So that's kind of what my job is to do, is kind of like, as I said, like, put the page numbers on this record that's in the rock if you know how to look for it.
Yeah.
That's awesome. That was a really good explanation. Okay, and then the last group is a professional at a conference. What do you normally pitch to people when you do poster presentations and things like that?
Expert.
Also, for that one, I would take it like the next step further. So what we do is, at least in my work, we have this kind of riffing off the one I just used, like this kind of stratigraphic record in time, and we're trying to put our little pins in time on rock. I think about taking the rock domain and moving it to the time domain, some kind of a version of a Fourier transform or something.
Yeah.
And to do that, though, all we have are these discrete points in time. And if they're dated ash beds, that's great. But actually, most of the time, we just have these maximum ages. So instead of being a pin, think of that as an arrow that just points younger. Or we actually like to think of them as like they're pushing up, because rock, deposits the bottom to the top. And so these, what we call MDAs, maximum depositional ages, are basically they're just push up against something. I mean, what you need to find is that pin in time. And so the next step to be a little more, rigorous about it is that we now run statistical models through these things. And so the biggest thing, it seems like in science these days, geoscience, is Bayesian statistics. And so we run these, so this paper I'm currently working on right now, through this stratigraphic section, oddly enough, not in the Grand Canyon, but in northern Utah, it has a fantastic record of this big excursion in carbon isotopes, which you can link to many different systems processes, sea level rise. Carbon isotopes are often linked to like extinction events or massive diversification events in life. And so we have this beautiful record of changes in the environment, but we don't really know it very well in time. We got it in the rock domain, we don't have it in the time domain. And so to do that, we're running what's called an age depth model, a Bayesian model, so kind of like a probabilistic. So basically the model takes these random paths through this rock versus time domain that's conditioned by these likelihoods. So you put in probabilistic ages, like we have our MDAs there, some probability distribution, but we have to pin them up with something. So we correlate by biostratigraphy in some pins from whales, oddly enough, which is the only other dated horizons in that part of the Cambrian from whales.
Oh, wow.
And so we put those in there as some kind of broad, because it's not very well known. I like to think of it as these ash beds are known well in time but not well in rock. And our MDAs are known well in rock but not in time.
Yeah.
And so then you have these, I like to think of it as kind of like blurry probabilistic ideas about where they are in the rock. So everything's kind of blurry. So you take your glasses off and you're looking at it. And so, but you can see these big blobs of, here's my MDAs and there's things. And so the rigorous way to do it these days is usually not deterministically, but probabilistically by using, this all like the hot button words these days, like Monte Carlo, Metropolis Hastings, all these like random walk models that run through it, and they try to basically predict the probability of your path, and that path then would be your time. So then therefore, even though I only have like 3 MDAs with this, using an age depth model, you can then have some type of better constraint on any horizon you want in there. You can pull out what the date probably is based on all the data. So basically, it's a way to amass tons of data together to kind of inform your model in a way. So that's what I'm working on right now, is ways to incorporate these different types of data into this modeling technique.
Cool.
So then we can pull out and be like, okay, you know what, like this excursion happens at this meterage and this meterage, and what's the difference between that would be our duration. And so that's what we're trying to get out. And then any other thing you'd want to, there's a big trilobite extinction event in there as well, so we're trying to pull out the actual age of that. And so it's just below our MDA. So if we run the model, it runs like a couple 100,000 times, 10,000 times, or whatever, and you pull out your confidence interval on that thing. And so that's the current way I think you tell time in the stratigraphic record, is taking your data and then putting it into this modeling technique to get at
Or the time constraints.
The duration, the rates, whatever you want of that.
That's really cool.
Of that stratigraphic sequence.
Nice.
I was actually about to ask you about modeling too, because usually you talked a lot about your explicit data, but there's always some type of modeling that's occurring. Are you building those models yourself, or?
So I'm currently now. So I'm using this like an R package that actually Robin Traylor, I don't know if you know the name. He was an old PhD student on the 5th floor from a couple years ago. So he's doing a lot of these like Bayesian Monte Carlo type models, and he writes them as R packages. And so I'm kind of taking that as kind of like my skeletal framework, I guess, and putting my data into it.
Totally.
To try to get the
Cool.
Yeah.
Do you?
So I guess I'm more of a user than a developer.
Yeah, and I think most of us are. So. Do you ever consider like the magnetic orientation of the rock at all for your timing?
Yeah, so that's the interesting thing. So yeah, like magnetostratigraphy would be a technique that's used, but it's not very. Yeah, so the interesting thing is, so in the Cambrian, which is, there's not really very good magnetostratigraphic constraints on that time.
Yeah. I know in general that record's kind of a mess.
Yeah, it's a bit of a mess.
As far as I know.
Yeah, that's kind of the tricky thing in the Cambrian. There's not a lot of, I think that's why it's kind of working that period is kind of not really evolved. Not to use. Probably it's evolving, but the work on the Cambrian hasn't really evolved.
Yeah.
Because there's not a lot of good, at least in this Western North America. There's not a lot of good time markers you can look at. Everything is like relative time. There's not a lot of absolute or numeric time, I should say. I don't like absolute. Nothing's ever absolute.
Yeah.
Numeric time.
Yeah.
Constraints you can use, yeah, because up in younger rocks like the Mesozoic and the Jurassic, Triassic, you look at like magnetostratigraphy, cyclostratigraphy, sequence stratigraphy. Those are all just much better developed in those sections. I don't even thought about why that is.
Yeah, why would that be?
Yeah, it has to be something to do with.
Could it be with like the recycling of like material though on the Earth? Like, is it just better constrained because like much more of that material is still available for those types of techniques?
Yeah, I mean that could be. Actually, you know what? This is. I don't know.
Yeah.
Interesting thought. I gotta think about it more. Huh.
Well, if anyone has an answer to that, you're welcome to to comment on one of our podcasts or reach out to us, or you know where we are if you're at Boise State, so come talk to us and tell us. Yeah, that's a really interesting question to think about. Well, really cool. This is all really awesome stuff that you do, Thomas. Like, I've learned a lot today. Like, I feel like I knew nothing about, like, I knew that you studied zircons, and I was like, okay, he's doing it for, like, dating some stuff, but I didn't know exactly what it was that you're doing, and now I'm, like, totally fascinated by your research, so.
You totally combine geo with chemistry stuff with a lot of physics, too, so you're...
Yeah,
it's broad. It's broader than I thought.
Broad,
Yeah. It's very cool.
Well, it's very specific, but it's like using a lot of like different things to like do that very specific science. So it's broad and specific at the same time.
Yeah.
So after I said that, I was like, it's not really that broad. It's like very specific.
Specific, yeah.
Yeah. Well, this has been an excellent interview. I'm going to sort of finish it off with some fun, silly questions for you. And I've got a few here. So I'm going to start out by doing a would you rather sort of component.
Okay.
So I'll ask you a few questions. So would you rather be forced to listen to the same 10 songs on repeat for the rest of your life, or forced to watch the same 5 movies on repeat for the rest of your life?
Whew. I guess the movies probably.
Me too.
Yeah, I think like
yeah.
The songs get old after a while.
Songs get old, and yeah. I mean, I do a thing where I get a song and I like play it to death.
Yeah.
And move on to the next one. But yeah, no, I listen to too much music to and I already rewatch a lot of movies anyway, so.
Yeah, that's true. Lord of the Rings, probably. I mean, there's 3 right there, so.
Yeah.
I'm okay with that.
Still got TV shows, right?
Yeah, true.
It's true, yeah.
And all the music available to you, so.
Yeah.
And podcasts. And
it would be so tragic for, like, long road trips to just have to listen to the same 5 songs.
I think it would take me my whole life just to pick the 10 songs I wanted.
Yeah.
No, that's the better one. But yeah, road trips would be hard.
Yeah.
Fun. Okay, next one. Would you rather have a time machine or a teleporter?
Ooh.
It's a geochronologist.
I know, yeah. That means I should do the time one. So I can go anywhere in time or anywhere in space.
And say the teleporter, like, you can stay within the teleporter, so you can go to, like, places where humans wouldn't be able to actually exist.
Or
just to make the stakes greater.
Back in time. Anywhere in time.
That is a tough one.
Oh, man.
Anywhere in time, but you stay exactly where the time machine was, though. It's like...
Oh,
so
so you're like stuck, like
Like you'd be
Basically-
stuck in Boise like
Oh.
250 million years
Yeah,
ago.
I guess I'd have to go with the teleporter then.
Yeah.
Go anywhere.
You'd probably be under sea actually
True.
at that
I
point.
guess
Yeah.
that's a good point. Yeah.
Yeah. Okay.
What about the future? Future would be so interesting.
That
to
would be
know.
interesting too. I know. No, it'd be too cool to go anywhere you want, but you can't leave the teleport. I mean, you can get out and like walk around.
Well, you can like if you use the teleporter to go to like the moon, then you
Right.
can't get out.
Right,
of
right,
it.
right. Okay. But if I want to like, it's cold, I'm gonna go to
Antarctica or something. Or, yeah, you
Go
You're gonna go to Florida.
Anywhere.
Go to Disney World.
Well, I don't know. I guess because if you go far enough back where there's like not enough oxygen in the atmosphere, then you can't step out of it.
That's
but-
true. It was just an interesting thing about that. They were like, one of the questions was, what do you think like the Cambrian smelled like? Was this one thing one time? And it was like probably like, think of it as being really like slimy and like I think of it like a bog basically, a
Ugh.
lot of decomposing. That's what they think. It was like very slimy and stinky place.
Yeah.
What's the age period where the bugs were really big?
Oh yeah, like the Carboniferous.
Okay, because I know
So-
that was when there was right now there's like 12% oxygen in the atmosphere. Back then it was like 30%,
Yeah,
like almost
yeah.
twice the amount. But like we would be able to exist in that, and I was just like recently listening to something that was like the inside of a greenhouse sometimes can have up to like 20 to 22% oxygen, just because it's like all those plants just like pumping oxygen in there, and it feels like great, but you can get like an oxygen high off of that. And,
Interesting.
yeah.
They used to have oxygen bars.
Yeah,
I
yeah,
know.
exactly. Yeah.
Is that still a thing?
Yeah, they
I
still
don't,
have
I don't
those.
know. They do.
Yeah, yeah.
That's funny.
If you walk around the strip in Las Vegas, they're like all over the place for some reason.
That's
I don't really know why.
They used to have them in college. I'm sure they still do because they're like, oh, you're at altitude. You need more oxygen.
Yeah.
Really? Cool. Would you rather never have a life without air conditioning, or never be able to use deodorant?
Wait, never have a life without air
I know
conditioning?
I think it's supposed to be never have a life with air
Air
conditioning.
Yeah, okay.
Okay, so either, let me rephrase. So either never have air conditioning.
Yeah, or never use deodorant.
That's an interesting thing, because if you pick never have air conditioning, does that mean like if we were in this room and the air conditioning's on, the moment you walk in here it just like shuts off or something? Like we're all subject to your like no air conditioning rule or something?
Yeah.
Yeah.
It's like you have to sign in.
Yeah.
Or it
just-
There's
it
like a
just
hot
turns off.
alert for
I don't
you.
know.
Like
So since I always have a fan on my desk, I do like it when it's cold.
Yeah, fan counts for air conditioning.
What, really?
I would
Okay,
say so.
no, yeah. I can't live without a fan or air conditioning.
Well,
What-
I was gonna say, like
no.
living without deodorant, okay, it might smell a bit, but also like you'd probably be healthier without
Yeah.
all of like the chemicals and
True,
stuff
yeah.
that you get through deodorant. So
Yeah, I would go with
and if you have air conditioning, you're probably not sweating as much.
You can still
hopefully.
shower and stuff too.
That's-
So
That's yeah. Hopefully, I love all the conditions we come up with
I know,
when
really,
we have these
yeah.
questions. Like,
the
like
proxies,
we
have
make
to-
it favorable in our
Yeah.
direction.
You have to make limits and proxies.
That's right.
Yeah. Oh, scientists. Okay, so kind of getting off of the would you rather, what is your favorite geological time? If you had to pick one, what would you say would be your favorite? I'm giving you all the hard questions.
That's a good one, though.
That's a good one. I've talked a crap ton about the Cambrian. Which seems like a pretty cool time. But I think okay, I wouldn't have to live there, right? It's just, what's my favorite time?
Yeah, like what's your time? Like,
Definitely.
yeah,
horrible.
no.
It might have to be, I might say the Cambrian, just because that's when it's quite a fascinating time for me. That's when,
Yeah.
I feel like the whole Earth is changing drastically.
I mean, trilobites are pretty cool.
It's pretty cool.
Yeah.
Although if I were to go visit one, making my own constraint here, I feel like it'd be cool to go back and like the mammoths.
Oh yeah.
Yeah, that'd be
I
cool.
want to check out dinosaurs. It'd be cool too.
Pretty scary.
Pretty
though.
scary. Yeah, I don't know. Like Jurassic Park. I'm like, oh god.
Yeah.
That's scary.
That can be one of the 5 movies.
There's that
that
one where they
you
drive around
watch.
the glass ball in one of the new.
Oh yeah, yeah.
That'd be fun. I
Yeah.
can do that. Like my
That's
time traveler.
Super Monkey Ball. Have you ever seen that?
Uh-uh.
There's a game called Super Monkey Ball where you're just a monkey in a ball and you just like roll around. that's always what that makes me think of. But what's your least favorite time period?
Oh man. I don't know. I haven't really thought about that.
The Holocene.
Yeah.
the present.
The present moment.
Today.
Today, yeah, just today.
Right now.
During this interview.
Yeah.
The moment you asked me that question.
Yeah, that's a tricky one. Every time somebody asks me a question like, "What's your favorite? What's your least favorite?" I always just like.
Yeah.
Yeah.
Mind goes
I
blank.
feel like I don't have sometimes I really don't have hard feelings about things. I don't know. There's this time in Earth history called the Boring Billion.
Okay.
Where it was between, I don't know, a billion and 2 billion years ago, where not a lot's happening.
Yeah.
But it's probably still cool. It's just basically just like bacteria making oxygen for 1 billion years.
Yeah.
Right on.
Yeah, we're doing good work. So
Boring billion bacteria.
Someone's gotta do it.
Boring billion, yeah, exactly. It's hard work.
Nice. What about you? What do you think, Brian?
I don't honestly know my periods that well.
Yeah,
to be
well, me
honest,
either.
So I guess probably I'd like to see when the very start. How about when the Earth was formed?
Yeah.
When
That'd be cool.
whatever object hit the Earth and created the moon, that period. I guess there'd be no life, but it'd be cool to see how the globe shaped from that. I guess all the debris outside that ends up coming back in and all that stuff. I bet the sky looked crazy at that time. So.
Yeah, and also the moon would have been a lot bigger.
Yeah,
back then,
closer,
so,
way
yeah.
closer, totally.
It's such a physicist type of
Yeah,
answer.
I guess so. I also don't know any specific names for the time periods.
Yeah.
Yeah, so that being period was called the Hadean,
Okay.
named after Hades, the god of the underworld.
Okay. That
Because it
makes a
probably
lot
would
of
have been
sense.
fire.
Oh yeah,
Lots
definitely.
of volcanic activity.
Probably no fire, no oxygen, but magma.
True.
Hot.
True.
Yeah.
Well, there might have been oxygen.
Could-
Maybe. Who knows?
So we gotta go. That's what I need the time machine for.
Yeah, definitely. Any major impact event, it'd be so much fun to go back and look at without any consequence of being
Oh
injured
yeah,
by
I've
it.
seen the Chicxulub impact.
Yeah,
That'd be fun to watch.
definitely.
I mean, do you think that from that impact things it was just, I mean, when we talk about catastrophic extinctions, I think people think of it as being instantaneous, everything just died right in that moment. And what are your thoughts about that?
It was probably prolonged, a couple
Yeah.
100,000 years, a million years, maybe.
Yeah.
Instantaneous for the ones that are right in that
right,
location.
Yeah.
Obliterated.
Well, yeah, if you're right underneath a meteor, probably.
Yeah. But our solar system is so stable now that you don't see those massive impact events anymore. But it'd be really cool to see that happen on a different planet, where they see something veering towards a planet and then they're able to just fully watch what happens with it. I don't think that's been observed yet. So
Yeah.
That'd be cool.
That's why we either need the time machine or the teleporter to
Yeah.
go find a solar system where it's much more in the path of objects flying into it.
yeah.
Which is a morbid thought, but
There's some area of space that has a super dense amount of stars. I forget what it is, but it's 100 times more stars are packed into the same amount of space as a typical area. And that place is probably pretty violent.
Yeah.
So
Yeah.
there's constantly a few years ago when they recorded those gravity waves passing over, it came from 2 stars colliding together in that cluster. So
What about rogue worlds, worlds that aren't tied to any they don't have a gravitational pull, basically they're sort of just floating around. What do you think?
it's hard to find those ones because you need the light from
the
a star to really find those. So yeah,
Weird.
it'd probably be really, it'd definitely be dark, cold, and
Yeah.
Yeah.
Not very
I'd use
fun
my teleporter to just go in the middle of outer space, I guess far away from anything, just to see what it looks like,
Oh,
with
yeah.
nothing around you at all.
That'd be crazy.
that dreadful feeling when you're like in the middle of the ocean and you don't see any land.
Yeah.
It's probably like that times 10. Or like down and
So
up
it's
too.
dark.
There's nothing.
Yeah, it's just dark.
You're like one of those. Have you ever done one of those sensory deprivation?
Oh yeah.
Have you been one of those?
Yeah, I have.
I have not. Is it?
I've done it twice actually. I like it a lot.
Okay.
Yeah, you just float there. It's like really salty water, so you float to the top. You're less dense than the water, and
Yeah.
like I turn off all the lights. Like sometimes they'll have music playing in there, and you just like float for an hour, and it flies by. It feels like 10 minutes, and you're out. And yeah, it's super cool. I definitely advise people to do it.
Okay. Yeah.
Well, Thomas, this has been absolutely amazing. Thank you so much for coming on the podcast and
really fun.
talking with us. Your research is fascinating. Your work is fascinating. We can't wait to hear about some of the results that you're finding and completing that book that you're trying to complete.
Oh yeah.
So thank you again, and we'll hopefully hear some more about like a lot of your research soon.
Yeah, I hope so. Yeah, Brian, Ashley, thanks a lot for having me on.
Yeah.
Appreciate it.
Yeah.
Stay tuned, everyone. We'll have another episode out in a few weeks, and thanks for listening.
Have an epic day. Well, that was an epic conversation.
We'd like to thank all of our listeners.
Tune in next time for another Epic Earth podcast.
I actually had trouble answering this question. This might get edited out. I don't know. The cryosphere and the well, not cryosphere. You should edit that out. Lithosphere. Yeah, I guess I would just say that. How would I say this?
I'll just cut out all this silence.
Yeah.
Yeah, you know, that's what I was figuring.
Yeah.
So I was like, I'm not worried about it.
Yeah.
Yeah, we're not worried about it. Come on, Thomas.
No, yeah, I
Put on the
three
Jeopardy
things.
music
I
or
should think about those.
something.
If there's a nice spot where there's like no sound and then you just like say something and then there's no sound after that, I might put the whole thing in the bloopers or something.
Okay.
But
Do some Jeopardy.
Yeah.
Music.
Yeah.